So I'll go to problem number 6. And problem number 6 is 2314. I have a sphere which is a solid metal sphere. It is solid, it's not hollow, and it's metal. And there is a charge plus Q on this sphere. And you're being asked, if the sphere has a radius capital R, what the electric field inside the sphere is, radius little r, and what it is outside the sphere. I will not assume, which is something we already know, that all the charge will have to be at the surface of this sphere. The reason is it's a conductor, it's a metal, and there cannot be any charge inside the sphere. That's not the case if the sphere were made of glass. Then you could have uniformly distributed charge throughout the glass, but not for a metal. But now I will first show you why that is the case. So I will distribute artificially the charge uniformly throughout this volume. I'm now going to calculate what the E field is at the location R from the center. I introduce a Gaussian surface, which is a sphere. It has a radius R, and obviously there would be an E field which is pointing radially outwards, and the elements ds are exactly in the same direction as E, this is ds, everywhere on this sphere, which is a concentric sphere. So I apply Gauss's law, 4 pi r squared, that's the surface area, times E. Forget the dot because the cosine of the angle is +1. That now must be the charge inside this sphere divided by epsilon 0. And this charge inside the sphere is not 0. And therefore, what's going to happen is there is going to be a force on the electrons. If I have an electric field and there are electrons, they will experience a force. But electrons in a conductor, in a metal, are free to move. So they're going to move under the influence of the force imposed on them by the electric field. And they will not stop moving until that force is 0. And that force will only become 0 when the electric field has vanished. So there is no electric field inside a conductor possible. The electrons would simply kill it. What is the conclusion? That the charge must all be at the surface. And I conclude that the E field for r less than r must be 0. And so now we'll calculate the electric field outside the sphere. I think we should make a new drawing for that. Radius r. And now I have a Gaussian surface which has radius little r, and the E field will be pointing out radially everywhere, and the ds's will be pointing out radially everywhere. And so it's very easy now to write down Gauss's law, 4 pi r squared E of r equals all the charge, which we know now is at the surface, uniformly distributed at the surface, Q divided by epsilon 0. And so we find that E equals Q divided by 4 pi epsilon 0 r squared. Famous results, inversely proportional to r squared. And this holds as long as r is larger or equal than r. And of course you can put in some numbers and then you'll get some answers. And this is always true. This is even true if this were not a metal and if the charges were uniformly distributed throughout. Then the answer outside the radius capital R would still be correct, because I have still applied Gauss's law. Of course, if this were glass and if the charges were uniformly distributed throughout, then the electric field inside the sphere would not be 0. Maybe you want to calculate what it would be as a function of little r. Maybe that's a nice exercise for you.